Okay, so we left off with this sentence that the point of inflection of a parabola, which is at the origin if the power of the power function is odd, is where the function changes its concavity. So this point of inflection, I want to just give you the German word for this. And concavity, I'll also give you the German word for. And I'll do a kind of aside in blue. Because this is just a little recap from last year. So if you remember, if we have a function that looks like this, then this function is known as a function that is concave up. And the German for this is very different from it being concave up. If you remember, we talked about driving along the function from left to right in the direction of the positive x-axis. If you imagine yourself driving along this road of the function in this direction, you'd have to turn your wheel of your car to the left, which is a helpful way of remembering that this is bended to the left, or concave up in English. And then, of course, in contrast to this, we have functions that look like this, which are concave down, for which we would need to turn our wheel to the right. So, of course, as you probably guessed, this is the German term for it. Now, if it changes its concavity, a function that changes its concavity changes from being concave up in part of the function to being concave down in another part of the function. So, a change of concavity could look like this. Let's really emphasize it. Where here we're driving along the function and we turn our wheel to the right as we carry along this road. But then, after a while, we're going to have to turn our wheel the other way to the left to carry on along the road. And there's going to be one point in here where our wheel is straight. So this point here, which is our point of inflection, is where the wheel is straight. And that's all this means, that if we have an odd parabola, then the function changes its concavity at the origin. So if you had a look and imagine driving along x to the power of 3 or x to the power of 5, you would find that your wheel would be straight at the origin. We're going to look into how to find these points of inflection and also vertices of different functions algebraically later on, but that's not something we need to do this year. This year we just need to be familiar with the terminology and also the look of different functions. So we've noticed now a few things where r is greater than 0, so when r is positive. If r is smaller than 0, however, let's go up a little bit. So for r being less than 0, then we have a few different things to notice. And you should notice that with all of the ones where r is less than 0, we have a very, very different shape to anything we've really seen before. So if we look at one or two examples, let's take f of x being x to the power of negative 2 and g of x being x to the power of negative 5, then we know from the rules of powers that x to the power of negative 2 is actually equal to 1 over x squared, and x to the power of negative 5 is 1 over x to the power of 5. And so what does this mean? Well, what happens when x is equal to 0? Well, clearly the functions aren't well defined. If we put 0 in here, 0 squared is still 0. 1 divided by 0 is mathematically impossible, so it doesn't work here. Again here, 0 raised to any power is still going to be 0 because you're just multiplying it by 0. So actually, it doesn't work for any of them. So this never works for r being less than 0. And that's why, if you notice in the graphs of the functions on page 30, if you go to where the origin to where x is equal to 0, and then take a look up and down the y-axis, you'll find that they never cross the y-axis, and that's because they're not very well defined. If I put one of these into a graph drawing program, let's hide that one for the moment, let's do y is equal to 1 over x cubed, let's say, then you can see that when x is 0, even if I bring the axis up really far, it never hits the y-axis. You can notice that it gets closer and closer to the y-axis, but it never hits it. And this would look exactly the same if I went in the other direction, in the negative direction. It would get closer and closer to this y-axis, but it would never hit it. And this then is a kind of invisible line that's part of the function but isn't actually part of the function because it's never part of the function. But it kind of looks like a line that we can see within the function. And this type of line that the function never hits but just gets closer and closer to is called an asymptote. So, for r being less than 0, power functions have a vertical asymptote at x is equal to 0. So they have this line that they never hit. So we could have down here and down here. And these are normally denoted by a kind of dotted line to show that there's an asymptote there. It never hits the vertical line. X is equal to 0. And you'll notice as well, for all of them where r is negative, we have a second horizontal asymptote along the x-axis as well. The functions never hit the x-axis. This one, if we take it in the negative direction, it's much harder to see. But if you zoom right in, you can see that it's not actually hitting this line. It might look like it is, but it's just very close to the line. And as you get further along, you need to zoom in more and more to see that there is some distance, but there is still some distance. And if it looks like it is on your calculator, you shouldn't necessarily trust it, because the resolution of your calculator is not necessarily large enough to show you whether or not it's hitting that axis. So, they have a vertical asymptote at x is equal to 0. Oh, let's change back to black. They also have a horizontal asymptote at y is equal to 0, or written in a different way, f of x is equal to 0. And that should be clear as well. If we take the example above that we had of g of x is 1 over x to the power of 5, g of x can never be 0, because if x isn't 0, then x is always some number. So you're always dividing 1 by some number. And as this gets bigger and bigger, of course we're dividing 1 by more and more parts, or into more and more parts, and so g of x as a whole is going to get smaller and smaller and smaller. But it's never going to be 0. I can never divide 1 by something and get 0 out. So that's because this has no solutions to g of x being equal to 0. And that's why we have this horizontal asymptote. Now, the functions that we had for r being greater than 0 all had a name. They were all parabolae. These functions for x being less than 0 also have a special name. So for r being less than 0, the graphs of the power functions are known as hyperbolae. And that's the plural of hyperbola. You won't hear the plural very often, you're much more likely to hear the singular. So these are all hyperbolae, this is a hyperbola. And you'll see as well that you can distinguish between the even and the odd negative numbers. So if r is odd, then you get this type of effect where you have 1 here and 1 here. And if r is even, then both of them are in the positive y range. So there's also a pattern to notice there as well. So now we've seen lots of different types of power functions and noticed some of the general properties of power functions, also whilst looking at a few specific examples. In the last couple of minutes, I just want to give you a quick definition of odd and even functions. And this is very much related to what we've been doing in the video so far. So a function is even if f of minus x is equal to f of x for all x. And this works very well with our power functions we've had, because if we have an example of an even function, say f of x is equal to x squared, any function with an even power has this property, because if I take negative 2 squared, that's going to be the same as positive 2 squared. So this is an example of an even function. So all even power functions are even functions because this holds for all of them. And it just means that if you have, for any value x and its counterpart, so here we have x and here we have minus x, they're going to give you the same y value. On the other hand, a function is odd if the opposite holds. So if f of minus x is equal to minus f of x for all x. And this works for all of our odd power functions. So an example of this would be f of x is x cubed, because then if I take negative 2 cubed, I get negative 8, positive 2 cubed, I get 8, and so the f of minus 2 is equal to minus f of 2. So for any odd power function, they're all odd because this holds. This is just something to note down, and next time in class we'll do a little bit of practice related to this as well. As always, if you have any questions, note them down, and please ask them next time or put them in your book for me to answer there. Hopefully, though, this has all been quite clear.